Today on Impossible Engineering, the Tokyo Skytree, the world's tallest tower.
It's a striking landmark, the world #1 tower.
To take structural design to new heights.
Now, if you don't get the foundations right, then that's a recipe for disaster.
Engineers must look to the innovative pioneers of the past.
This is unbelievable. This rocket is just so big.
To make the impossible possible. Tokyo, home to over 35 million people. With suburbs stretching 14,000 square miles. Its vast sprawl of low-rise buildings is a direct result of one singular environmental challenge: earthquakes. But for the first time, as space in this mega city runs out, engineers must now look up. As taller buildings rise, an unexpected challenge emerges, especially for the city's nearly 1,100-foot tall communications hub, the Tokyo Tower. Everyone here, including high-rise architect David Malai, can clearly see the problem.
You can almost see it's going to be blocked out by a building. The signal's being blocked.
In a nation that experiences 1,500 earthquakes a year, uninterrupted TV and radio communication is vital. This problem requires a radical solution.
Here it is, Tokyo Skytree.
Unprecedented in Japan, the Tokyo Skytree is the world's tallest freestanding tower.
It's double the height of Tokyo Tower. It's got the most advanced engineering and technology we have available today. This is the solution for Tokyo's connectivity.
For designer Tetsuya Tsuchiya, scaling these heights offers a unique challenge.
I think all the architects and engineers have some dream to create, something high and something, going to the sky.
The record-breaking 2,080-foot-high structure is more than 4 times the height of the Great Pyramid of Giza. Its spine is a 1,200-foot hollow concrete core, cloaked in a 37,000-piece steel frame, which morphs from a triangle to a circle. It has 2 observation decks. The tallest, at almost 1,500 feet, is one of the highest in the world. And it's topped by the state-of-the-art antenna tower, capable of transmitting 62 miles away. Construction begins in 2008, but before Skytree can even rise above the ground, its designers face a seemingly impossible problem.
Where we are now used to be part of Tokyo Bay. The land I'm walking on was underwater. So what that means is the soil around here is extremely soft. And for engineers, this presents a big challenge, especially when you do something of that height in a place that has earthquakes and typhoons. It's going to want to push the building, so that building needs to be firmly anchored into the ground. Now, if you don't get the foundations right, then that's a recipe for disaster.
With this colossus exerting over 75,000 tons of force, how can you ensure it will remain standing on unstable soil during an earthquake? To accomplish the impossible, engineers must look to the past. It might be far from perfect, but soft ground has rarely scared away history's engineers.
Oh, forget it.
Olé! In fact, some of the world's most famous cities have been built on swamps and marshes.
Bravo.
In New Orleans, the ground is so soggy, the city famously had to build their cemeteries above ground.
That's better.
And Berlin is crisscrossed by a constantly changing 40-mile network of pink pipes used to pump the ground free of water.
Wunderbar.
Architectural historian Jen Mazengarb is exploring San Francisco to find out how the 1848 gold rush ultimately sparked an engineering revolution. To serve this booming Bay Area, architects constructed the monumental New Ferry Building.
It weighs about 150 million pounds, which translates to about 75,000 tons.
Not only does it stand in a seismic zone, the building's 245-foot tower and extreme weight both rest on 180 feet of bay mud, creating near impossible building conditions.
So those tasked with designing a new ferry building really had to think about innovative solutions in order for the building to be successful.
To support this grand architectural design on unstable grounds, engineer Howard Holmes had to look beyond traditional methods and dig deep.
I've got some wet sand, which is the same kind of sand that's here underneath the ocean. And this wooden plank is to help us see that concrete mat that the entire building is sitting on. And these nails are those wooden piles that are driven down to the sand. In a typical building, you might use only as many piles as you would need to support the building. So let's see if that works. I can put quite a bit of load on this, but we're in a seismic zone. You can see that I can turn this sideways pretty easily. So wiggle, wiggle, wiggle.
But to survive earthquakes, the new ferry building needed something more.
So here's my new demonstration with lots of piles. Wow, not only can I not push it in very much, but when I try to wiggle it side to side, I really can't.
And the secret of this stability is due to the friction.
Friction is created around the surface area of each of these piles. And more piles equals more surface area. And because it's much more stable like this, any earthquake load, all of those forces are just going to be absorbed by all the piles, making the rest of the building much more secure. Brilliant.
Over 5,000 wooden piles extend deep into San Francisco's semi-fluid sandy mud. These support the structure's 111 concrete piers.
It's a foundation with 3 parts, which you can see here. A reinforced concrete mat under the whole building, then concrete piers, then wooden pilings driven down to the mud. Those wooden pilings are about 80 feet in length. Underneath the tower, there are 345 piles alone.
Completed in 1898, the new ferry building continues to defy sinking sand to this day and anything else that nature throws at it.
This design has withstood the earthquakes of 1906 and 1989, both of which caused massive damage throughout San Francisco. The building has proven itself through its innovative engineering.
At the over 2,000-foot-high Tokyo Skytree, engineers take Holmes's revolutionary method into the 21st century. To stabilize it, workers drive 131 concrete piles into the soft ground. But the building's record-breaking height adds a further problem.
When the big forces apply to the tower, like a typhoon or big earthquake, the entire tower acts like a giant lever and put enormous force on its base, pushing up one side and pulling up the other.
To compensate for this, Skytree needs a unique system. Its 75,000 tons of force is exerted onto a tripod-shaped base. 160 feet below the surface, 3 clusters of 4-foot thick walls use friction with the surrounding soil to increase horizontal rigidity. 3 160-foot wall piles connect each cluster, with added knuckles acting as spikes, further increasing friction. Combined with the column piles, the tower's foundations act like a tree's roots, bracing the superstructure for even the most extreme of conditions.
Friction between the wall and the ground soil acts as an anchor. This is a very special foundation system exclusively used for the Tokyo Skytree.
But to complete the world's largest freestanding tower, engineers must look to the past.
It's a brilliantly simple solution and sparked a renaissance in skyscraper construction.
To make the impossible possible. Soaring over 2,000 feet, the Tokyo Skytree is the tallest freestanding tower on the planet.
It is the world's tallest tower in one of the world's busiest cities. So it was very challenging work for us to construct.
More than 6 times higher than London's Big Ben and twice the height of its predecessor, the Tokyo Tower, Skytree is changing the face of Japan's capital. But as high-rise architect David Malott reveals, building to this height in this highly congested city poses a unique challenge.
The engineers at Tokyo Skytree had to put a tower that's twice as high as Tokyo Tower on a piece of land that's only a quarter of that size.
The proportions of a super tall tower are crucial. If a structure is more than 5 times higher than its narrowest base dimension, it can become unstable in the wind. But Skytree's ratio is a daunting 9-to-1.
It's one thing to build tall and wide, and it's a much more challenging thing to build tall and slender.
So how do you build a super slim, record-breaking tower on such a confined plot of land? Engineers have always been able to build short and fat. And after a while, they mastered tall and fat. But building tall and thin has often been a problem.
Are you sure? Go for it.
Ireland's highest round tower is an amazing feat,
I told you, perfect.
but isn't exactly straight. The first St. Mark's Campanile in Venice certainly looked the part.
Mamma mia.
But the impact of the weather and the weight of its 5 mighty bells led to disaster.
We're going to need a new tower.
Engineers had to return to the drawing board. During the 1920s, Chicago became synonymous with skyscrapers. By the 60s, with space increasingly at a premium, developers wanted to build even higher. But traditional, bulky construction methods were stifling their ambition. However, in 1968, engineer Fazlur Khan came up with a game-changing solution.
All right, thanks.
And architect Jayshree Shah is here to get a bird's-eye view of it.
This is the groundbreaking building that Khan was working on.
Over 1,100 feet high, the Hancock Center was the first skyscraper in Chicago to reach 100 floors. But this impressive building sits on a footprint 27% smaller than the city's second tallest skyscraper from that time, the Chase Tower. So, how does the Hancock Center continue to stand in the face of Chicago's legendary wind?
Just take a look at this skyscraper-shaped tower. If I push on it just a little bit, like a lateral force similar to the wind, you can see how much it bends. Now, if I push even more, you can see how it begins to twist. Oh, jeez. All right, I broke it.
But the simple addition of 45-degree cross braces changes everything.
You can see how much stiffer it is. When I push against the building now, it's not bending or twisting as it did before.
Called braced tubing, Kahn used this technique to reduce the horizontal loads on the building. As the winds pushed against the building, their force now transferred down the diagonals to the base of the structure, easing the load on the building's vertical columns.
Fosler-Kahn's brace tube design sparked a renaissance in skyscraper construction.
Engineers at Tokyo Skytree are drawing on Fosler-Kahn's genius brace tube design to create a record-breaking super slim structure that dwarfs the city.
Steel bracing structure is very important to stabilize this tall and thin structure.
In an area renowned for typhoons, building a tower almost double the height of the Hancock Center on a footprint 51% smaller requires both brains and brawn. The 37,000-piece steel framework consists of 3 layers with thousands of triangular trusses. Immensely strong, this steel curtain can resist wind gusts approaching 250 miles per hour.
This outer steel frame carries all the weight against the strong wind. You can also see through it so that the wind can pass through the tower so that we can reduce the wind load.
As well as defying the odds, its designers have also created a shape that makes Skytree totally unique.
The shape of this tower is characterized by the triangular shape at the foot, and gradually transformed into circular shape to the top. That came from traditional Japanese architecture, so gentle curve, the maiden structure.
But to brace for more daunting challenges, the Skytree team must turn to the past and reach for the stars.
It was a beautifully simple concept that ultimately helped push our exploration out into space.
To produce more impossible engineering. At over 2,000 feet, the Tokyo Skytree is the world's tallest freestanding tower. And with it, architect Tetsuya Tsuchiya is redefining Tokyo's skyline.
People can see this tower, and also we can see the city. So I think it's a really great viewpoint to really understand the city of Tokyo.
But as high-rise architect David Malott reveals, building to this dramatic height here means engineers must conquer a seemingly impossible problem.
Japan is part of what we call the Ring of Fire. So it's one of the most active seismic zones in the world. So earthquakes are a part of daily life here in Tokyo.
It's a very big challenge for us to control the swing and the movement of this tower.
So the engineers of Skytree were tasked to build not only the world's tallest television tower, they had to put it in what is probably the world's most dangerous location.
In a country that endures around 1,500 earthquakes a year, how do you ensure a super tall tower will remain standing? To overcome this challenge, engineers find inspiration in an unlikely innovation from the past.
Launch commit. Liftoff. We have liftoff.
Space historian Amy Shira Teitel is in Florida, at the home of one of history's most awe-inspiring endeavors.
This rocket is just so big. It's so great.
Since the 1960s, Kennedy Space Center was the launch pad for NASA's epic Apollo space missions.
This is really amazing to be standing here. This is launch pad 39B. This is where the Apollo 10 crew launched and went all the way to the moon to orbit before coming home. At the moment of launch, the 5 F1 engines together produced more power than 85 Hoover dams. The sound of the launch was so intense, they actually had to dump 3 million liters of water onto the pad every minute just to dampen the sound waves so they couldn't bounce back up and rip the rocket apart.
Just like old times. It's beautiful out there.
But achieving such an explosive liftoff called for a lot of energy. Almost 530,000 gallons of rocket propellant was needed to get the over 360-foot rocket off the ground.
Delivering all that fuel to the rocket required umbilicals, masses of cords and wires running all the way up the service structure.
Attached to the rocket by spring-loaded swing arms, it was essential the umbilicals remained in place until the very last second, before an electrical discharge jerked them and the swing arms back towards the launch tower.
However, the challenge was controlling the swing arms' sudden, powerful movements. They had to make sure they wouldn't break off from overexertion or bounce back and hit the rocket as it left the launch pad. Thankfully, there was one engineer working on a solution.
To address this problem, former Air Force engineer Paul Taylor worked alongside NASA. His patent for an innovative shock absorber design offered a breakthrough for the Apollo mission's tricky launch procedure.
The concept Taylor came up with was the fluid damper or the liquid spring, and it works something like this. Now imagine that this coffee press is our fluid damper, and it's sitting between the tower and the rocket. You can see that when our damper is empty, it offers very little resistance to weight or the force of the swing arm when it's released. But if you fill it full of fluid, look at the magic of the green liquid. And if you put the weight back on, you can see it compresses much more slowly. So what's happening is, as the plunger is pressed, the liquid is forced through the holes. This creates resistance, which dissipates the energy, which makes the plunger move more slowly.
During a launch, as the umbilical-laden swing arms spring back, the attached fluid dampers are compressed, and the fluid inside them is forced through holes in the piston. This action creates friction, which slows the arms down to 0 speed at the end of travel and minimizes risk of damage to the tower or rocket. In 1969, Taylor's ingenious system proved its worth as Apollo 10 safely launched on its pioneering mission to orbit the moon, making its mark in space travel history.
We are go for a mission to the moon at this time. We have ignition sequence start. All engines running. Launch commit. Liftoff.
Taylor's hydraulic innovation has stood the test of time and is still in use today, protecting sensitive equipment during launches to the International Space Station.
It was a beautifully simple concept that ultimately helped push our exploration out into space.
But using fluid dampers to brace the world's largest tower against earthquakes is an altogether different challenge. To do this, the Tokyo Skytree team must make revolutionary innovations.
This is the first one in the world.
To make the impossible possible. The Tokyo Skytree is the tallest freestanding tower on the planet. But at over 2,000 feet, engineer Atsuo Konishi and his team must brace it against a potentially devastating natural phenomenon.
In Tokyo area, the big earthquake occur. That is a challenge for us to design such a high-rise structure.
To stabilize the tower, engineers rely on fluid dampers developed during NASA's Apollo space program and from something closer to home. The engineer's first step in controlling the shake of the tower centers around an ancient earthquake-proof structure called a Japanese pagoda. A flexible earthquake-dampening central pole called a shinbashira stabilizes this tiered wooden structure. Skytree's engineers are emulating this ancient technology, creating an enormous 1,200-foot concrete column set on 6 giant rubber bearings.
Now we are here at the bottom of the core column. I came up with a core column system because there is a shinbashira in Japan.
And sandwiched between this mass and the tower's steel structure lies the Apollo-inspired fluid dampers.
The upper half of the core column is connected with oil damper to the steel structure.
Situated between 410 and 1,230 feet, the series of fluid dampers control the movement of the freestanding 11,000-ton concrete core and the steel exoskeleton throughout a seismic event.
During the earthquake, the core column designed to shake just a little bit slower compared with steel towers. That condition is a reason why the core column system reduced the vibration of the Tokyo Skytree.
The different vibration cycles of the central column and steel frame can counteract the vibration of the entire tower.
If the oil damper isn't installed, the core column will collide the steel structure. The core column will collapse.
The system is so effective, it reduces an earthquake's vibration by 50%, meaning Skytree will survive Tokyo's most severe seismic activity, the likes of which is only expected once every 1,000 years.
The vibration control system is a unique system for Tokyo Skytree. This is the first one in the world.
But as well as standing firm during a magnitude 7 quake, this state-of-the-art communications hub must also continue to transmit its signals. And to do this, any vibration of the 460-foot antenna tower must be made practically still.
The swaying of the antenna has a really bad effect. The movement of broadcasting tower is allowed only a few centimeters, so we have to control the swing.
So the team introduces a secondary vibration system at the pinnacle of the tower.
To control the swing and the movement, we have tuned mass damper buried at the top on the antennas.
The tuned mass damper contains a 45-ton concrete block, which moves like a pendulum. During an earthquake, there is a time lag between the vibration of the tower itself and the movement of this concrete mass, canceling out the vibration of the main structure, resulting in a super stable antenna system. It can still transmit even during Tokyo's most extreme seismic activity.
Without this system, our broadcasting cannot continue after the big gasquake.
Skytree's breakthrough engineering has tamed one of nature's most devastating forces. But to complete this mammoth super tower, the design team faces even more formidable challenges. And they must draw on another great innovation from the past to produce more impossible engineering. The Tokyo Skytree is setting a new benchmark in high tower design. As a communications hub, the over 2,000-foot tower can transmit up to 62 miles away. But for its architect, Tetsuyo Tsuchiya, this engineering colossus stands for so much more.
The Skytree has two major functions. One is, of course, this is a broadcasting tower. And at the same time, this is a very interesting observation tower for the tourist. So getting here and enjoy the view is the most important thing in this tower.
But as high-rise architect David Malott can see, creating a bird's eye view in a tower this high poses tremendous technical challenges.
When you're building observation decks, it's going to be subjected to tremendous force from typhoon.
The wind speed here up above is maybe 50% stronger than the ground level. And it was very important that any guest feel safe during their visit, even in bad weather or any earthquakes.
To offer these breathtaking views requires one resilient material: glass. But how do you ensure the glass will remain in a safe state in the face of typhoons and earthquakes? This would have been impossible without a chance discovery made in Paris over 100 years ago. Scientist Suzy Sheehy is here in Paris to discover how the city's notoriously bad traffic inspired a transformation of safety in the modern world.
In 1903, driving was fast becoming the hot new hobby among Parisians. But like today, the traffic was congested and dangerous, and accidents were commonplace. It sparked an idea that will go on to change the world.
Born in 1878, scientist Edward Benedictus studied chemistry in Germany before setting up a laboratory in Paris, where he made his breakthrough discovery.
Car windscreens were causing drivers serious injuries in the case of an accident. The windscreen would smash into shards, which in some cases proved fatal.
Incredibly, Benedictus discovered a solution to this concerning problem entirely by chance.
During some routine testing at his lab one day, Benedictus accidentally knocked a glass flask off a shelf. And remarkably, instead of smashing into 1,000 different pieces, it actually maintained its shape.
Examining the shattered flask that had mysteriously remained in one piece, Benedictus observed remnants of a liquid plastic within the vessel and concluded that its thin coating held the broken glass together.
Benedictus had a brainwave. He realized that this plastic-coated glass had the potential to save lives. So this is a piece of laminated glass, And it's like the modern evolution of Benedictus's discovery. It's basically just two pieces of glass which are bonded together with a piece of plastic between, which holds it together. And over here, I also have some pieces of just normal sheet glass. And this is similar to the glass that would have been used in a car windscreen in Benedictus's time.
To see how each one reacts under impact, a 4.5-pound steel ball is set 13 feet off the ground. First up, the normal sheet of glass.
Ready to go. Okay, so this piece of glass is really smashed. You can imagine how dangerous one of those sharp shards of glass would be if it came flying at your face during a car accident. So instead, let's try a piece of laminated glass and see what happens. All right, place my laminated glass now. But this time, I'm going to raise it up higher.
With the drop height raised to 20 feet, will this laminated glass withstand impact? And how will engineers employ this technology against the fury of Mother Nature? As the world's tallest freestanding tower, the Tokyo Skytree offers stunning views of the city. But to create a safe viewpoint at this dramatic height that can also withstand typhoons, engineers draw from an early 20th century breakthrough in glass design.
Let's try a piece of laminated glass.
To test its strength, Dr. Susie Sheehy raises a 4.5-pound steel ball to a drop height of 20 feet.
Whoa! It actually didn't go through. Oh, wow. Okay, so my steel ball managed to form a beautiful spiderweb pattern on here. And the glass has actually stayed in place, stuck to the plastic in the middle.
Benedictus's layered glass is so resilient because the lightweight plastic stretches when struck, absorbing any force and offering a tear-resistant barrier.
So it's a pretty simple invention, but it's made the roads a much safer place.
Engineers at Tokyo Skytree are using Benedictus's ingenious layered glass to take on Tokyo's powerful typhoons.
This is a very tall tower, so the wind is very strong here. If you look at the building down there, the wind pressure here is almost double.
With two 360-degree observatories and one of the highest skywalks in the world, incorporating a glazed floor, each of Skytree's 1,027 panels of glass must be super strong.
We are in the 450-meter level. Today we are in the cloud. And these are the glass panels.
Installed from the inside and integrated into steel curtain wall framing, this state-of-the-art laminated glass can withstand winds in excess of a mind-blowing 325 feet per second.
These glass panels are with the 2 layers of double-strength glass pane. In between it is this polymer membrane. It is called the layered glass. It is super strong to withstand a strong wind. Even if the most powerful typhoon came, this system is very safe.
The Tokyo Skytree Temple Galleria.
Because of the pioneering work of Benedictus, even in the unlikely event the glass does shatter, the panes will remain in place, allowing around 4.5 million people a year to safely experience one of the greatest vantage points on the planet.
I always come back here and see people enjoying the great view, and that makes me very happy to look down the city.
Completed in 2012, this audacious architectural marvel was constructed in under 4 years. It stands as the result of ambitious planning and testing by thousands of engineers.
It is very proud for me to work on this project.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers have written a new chapter in high-rise design.
Since the very beginning of the civilization, taller structure has always been a dream of human being. So constructing the world's tallest tower is one of the most exciting and challenging jobs that any engineers can engage.
They have succeeded in making the impossible possible.
Tokyo Skytree is a striking landmark. It's really a combination of state-of-the-art Japanese construction technology and also the very old Japanese wisdom of creating very tall tower.